Let's explore a maximization problem, maximum t0 to t1 of the same function f tx x prime dt over x in u, but this time here is how the set u is the set of functions in C1. We have C1 functions over the interval t0 t1 that satisfy initial condition t0 given, and xt1 free that is belong, so we say it's free, is free condition. Okay, so our purpose is to find necessary conditions. So the first thing, necessary condition. So the necessary conditions So if under, of course, the assumption that f is C2, okay, under the same assumptions we saw previously, previous section. Okay, so yes, if x star is relative, is a solution of the problem in U, then necessarily we have Euler equations. So let's before, yes, necessarily Euler equations are satisfied. Okay, so dx dt, df dx, then so let's write them here. df dx minus d dt of df du at t x prime equals 0. That is, those are Euler equation, and we will have we have a transversality equation. So we show that the derivative df du, okay, at t, okay, df du at t, okay, at tx x prime, okay, applied at t equal t1 equals 0. So this one is new, equal transversality condition. So necessarily, if my solution is, if x star is solution of maximization problem in the set U, then necessarily we will have Euler equation and transversality condition. That means if we are looking for our candidate points, necessarily there will be among of solution of this set. Okay. Now there we have also, we show also a sufficient condition. Sufficient condition is a condition that allows us to conclude that the point is a solution of the problem. So that's about Euler and appropriate transfer. So if we have so here this time, if x star satisfies Euler and transversal Euler equation and the transversality condition, plus f is concave in xu, then x star is a solution. Okay, solves the problem, solves the max problem. Okay, above. So this is, we don't have to technique. The proofs are similar to the first case when we had both the condition. We looked at in the space xt0 equal x0 and xt1 given equal to x1. So the two results are, the proof for those two are similar. So we don't have to go through them. Let's more practice. Look at an example where we can solve the problem. Okay, so let's do that. So maybe I will use so this one. Yes, why not? So let's do this one. Here it is. An example. Sorry. So let's start then. Solve the following example. So the example says to find the solution, solve the problem. Maximization problem 0 to 1 of 1 minus x2 minus x prime square dt and x0 equal 1 with x1 free. So this is the question. So let's identify all the steps, the type of problem we are considering. So we have a maximization problem, yes. So in type we see that we have a function ft xu. I can identify it, it's minus x2 minus u2. The space I'm looking for, I will look for my solution in the set of C1 functions from so t0 1, where x0 is 1 and x1 is 3, so it belongs to, is a real number, any real number. I create, then I will need fx, partial derivative minus 2x, fy I will need it, fu I mean, fu is minus 2u. Now I will need the derivative of t of fu at t x prime. So let's identify what is fu at t x prime. So the role of u is applied by x prime, so it's minus 2x prime. Therefore, when I derive this quantity, I need to derive the dt of minus 2x prime, which is minus 2x second. Now, if the candidates, let's look for the candidates for optimality. I will maybe need to work here. Let's continue here. Okay. Yes, the candidates. So Euler equation first must be satisfied. Euler equation. So let's write Euler equation. I have my partial derivative, so it's fx minus ddt of fu applied at tx x prime equals 0. So fx, we said it's minus 2x minus the derivative ddt of fu, it's minus 2x seconds. Okay, so everything I did already, the calculation, the derivative. So it's minus 2x second equals 0. Okay, so x second, okay, that is, we have the equation x second minus x equals 0. Okay, so this is a method to solve ordinary differential equation. So we look for the characteristic equation. We assign r square minus 1 equals 0. So we have two roots, r equal minus 1, r equal 1. The general solution, this homogeneous equation. So xt is equal a exponential t plus b a minus t. A and b are constants. Use now the factor the transversality condition. So let's express the transversality condition. Yes, transversality condition. Let's write it, use another color. Now the transversality condition, let's express it. So it says it's the derivative of its fu at t x prime applied at t equal t1 must be 0. So fu, we found it, fu is minus 2x prime at t equal t1 here is 1. Is it 1? And, we are looking for, yes, is in the interval 0, 1, t equal 1, it must be equal 0. So that is x prime at 1 equals 0. Now we have the general, so we have the general solution. X prime t is a t minus b a minus t, so that x prime 1 will be a minus b a minus 1 equals 0. So we need this relation between a and b. Let's express now something we didn't do, the initial condition. So my solution x I'm looking for belongs to u, therefore x at 0 is given, and here it says that it is equal to 1. It is equal to 1. Now x 0, so it will be then a plus b, so must be equal. So identify now, let's identify a and b. So we have a system a plus b equal 1 and a exponential minus b a minus 1 equals 0. So we can deduce then the two possible values for a and b. So we have a equal then from here, so we can identify a as 1 over 1 plus a squared, and b is 1 minus a. That's e2. Okay, now that we have this, so which is e2 1 plus a squared. Okay, so we have the general, we have x star. Okay, we found x star. Now this is the candidate. Okay, x star is the candidate. Now is it the solution? Okay, so we use the second, then we explore the concavity. Explore the concavity, then yes, why not? So let's concavity of f in xu. So my function f, what is it? So we have all the fx and fu. So fx is minus 2x and fu is equal, so let's have a look at it. It's minus 2u, so that I can compute the Hessian of f in xu, okay, as function in xu. Then it will be fxx, fxu, fux, and fuu. So which gives me minus 2, minus 2, fx u0, 0 and minus 2. So it is clear that d1 at xu is equal minus 2. So minus 1, 1 d1 xu is equal to positive, and d2 at xu is 4, and minus 1 to d2 at xu is 4, it's positive. So yes, f is concave in xu. Therefore x star t, that is defined, so we said it's a and b, so a is 1 over plus a2, so at plus b is a2 minus t, okay, and the put it the factor is solves the problem, okay, solves the max problem in U. So we found yes, the solution. So this is how you apply those two theorems, okay. So this is so the variant of the other problem. The only thing that changed is the set U. So changing the set U, we had a new condition, necessary condition that should be satisfied. So the candidate should necessarily be looked for here in this system, okay. Once we get the candidates, if we have concavity, then we can conclude that this is the solution.